on Unifying today. I'll share my screen. Okay. So I'll be talking about the Unifying data structure today, which is pretty useful for several applications. And I'll just get started now. Okay, so what is the Unifying data structure? So the Unifying data structure is basically something that keeps track of a set of elements that is split into a bunch of disjoint subsets. And this data structure allows one to find which subset a particular node is in, and then also to merge two nodes into one subset. And it does this in all, it does these operations in new linear time. I will explain what I mean by new linear time later. New constant, yeah. Yep. So what would we use this data structure for? So suppose there is a graph question that wants to answer two types of queries. One is to basically join two nodes with an edge. And another one is basically asking how many connected components are there. With this data structure, we can perform in each query in near constant time, and this is very useful. Okay, so let's go into how does it exactly work. So basically, the data structure has an array, which is called parent, which stores the parent node for each node. At the start, before any operations, the parent node for every single node is simply just itself. So, but when two components are merged, the node whose parent is itself, known as the representative node, sets its parent to the other representative node. So I'll clarify the statement. So basically, like each node in the data structure, if you follow its parent, if you set it to its parent and then set the parent to its parent and repeat this, eventually you'll end up at a representative node where the parent is itself. And this representative node, as suggested by the name, represents the entire set. And so when you merge two components, you want to set one represented node, its parent, to the other representative node. And this effectively joins all the nodes from one component to another. And yeah. So here is an example. So suppose there are two nodes, 0 and 1 here, and we want to merge them. So initially 0's parent is 0 and 1's parent is 1 because no operations have been performed on them so far. And then to merge them, we simply set the parent node of 0 to 1. Or in this case, you can also set the parent of 1 to 0. It doesn't really matter for this specific example. And so now both of the parents are 1 or 0, depending on what you just did. And the two are now merged. And suppose we want to merge the two components on the right. So currently the parent array is 1 for node 0 because we're treating 1 and 4 as the representative nodes. So 0's parent should be 1 and 1's parent should be 1. 3's parent should be 4, and sorry, 3's parent should be 2, 2's parent should be 4, and then 4's parent should be itself, because 4 is the representative node of the component on the right. And we basically join the two components by setting one representative node's parent to the other. So we set the parent node of 1 to 4. So after that, in terms of the diagram, we'll essentially be drawing an edge from 1 to 4, and 4 becomes the representative node for everything. And we can see this in the new resulting parent array, which is 1, 4, 4, 2, 4. So basically, node 1 now points towards 4. And now everything is connected. All right, let's look at one of the methods we had to implement for the disjoint set data structure. So find is a method to find the representative node of a particular node. So the time complexity of this, without any optimizations, worst case is O of n, but I'll present ways to optimize this in later slides. But for now, what this method does is check if the current node is the representative node. And we do this by checking if its parent is itself. If it is, that means it is a representative node, and we just return it. Otherwise, we return the parent, the representative node of its parent, which should be the same thing. And it will eventually go to the representative node, because the representative node is the node at the top of the component. So if we traverse along the parents, obviously it'll keep going up until we get to the representative node. Again, I'll present ways to optimize this later. So here is also a naive merge method. This merges two components in O of n without any optimizations. It's O of n because of the find methods. And what this method does is that it finds the representatives of two nodes and sets the parent of one to another. So basically in this code, x root is the representative of x, y root is the representative of y. And if they are the same, there's no need to merge them because the representatives are the same. Otherwise, we set, in this case, we set the parent of x root to y, but you could also set the parent of y root to x. For the naive method, this doesn't matter. Yeah. So now we get to the optimizations. So previously, we learned how to implement these methods in O of n, but we can do much better than that. With one of path compression and one with either path compression and union by rank, it brings the complexity down to O of log n. But if you do both, it brings it down to near constant time. And I'll do a complexity analysis again at the end. But for now, just when using one of them, it's O of log n. So here's path compression. To apply path compression, we just make a tiny change in the find method. And we basically, every time we call the find method, the parent of each node on the component is set to the representative node. Actually, this is technically false. It's only the parents of each node that we traverse going up to the representative node. Their parents are set to the representative node. And for all future calls of find, we only have to call recursion once because the parents are of all the nodes that we traversed are the representatives. So obviously this makes it more efficient. So you might be a little bit confused about why this does this, but basically find returns the find returns the representative node, right? So by assigning it to the parent of X, it automatically just assigns the representative node to the parent of X. And I will stop sharing this for a moment and I'll draw a diagram real quick to show this operation. One second. Okay, so suppose we have suppose this is the structure so far. And suppose we call the find function on this node, then the resulting like structure would be this. Basically, it compresses the path for each of these nodes into only one recursive call. And this obviously makes it more efficient from now on. Okay. So that's path compression. And here's union by rank. So we keep an additional array of size n called rank. And we make the following modifications to the merge method. In this case, we call it union, but it's still the merge method. It's the same thing. So firstly, we find x root and y root again using the find method. And then if they are the same, we don't need to merge them like last time. And if a rank is less than, actually, first I'll define like what rank actually is. Rank in this case, in this code, keep track of the depth of the component, the depth of the lowest node in the component. So it attaches the component with smaller depth to the component with bigger depth. So all computations in the future, all find methods have less depth to go through. And so here, if the depth of x root is less than the depth of y root, we attach x root to y root and vice versa if it's the other way around. Otherwise, if it's the same depth, we have to increment the one of the depths by one, and we arbitrarily just attach y root to x root, and then increase the depth of x root by one. This is not the only way to implement union by rank. You can also implement it using union by size. And as said on this slide, it results in similar performance. They're both logarithmic log time, and yeah. So the time complexity is even lower when you use both path compression and union by rank at the same time. It's O of Ackermann of n. And the Ackermann function is basically, I obviously won't prove why it's this time complexity, but you can just memorize it. And the Ackermann function grows very, very slowly. So So you can basically treat it as a near constant time operation. And like, I believe it doesn't exceed 4 until you get to like an input size of 10 to the 600, which for typical programming problems, you obviously will never encounter. So you can just basically treat it as constant time operations. Okay, and here are some practice problems using the unifying data structure. A lot of times this data structure is just used in conjunction with the Kruskal's minimum spanning tree algorithm, which I believe Yifan presented in an earlier lecture. And I think he did mention this data structure, but I just presented it in more depth today. And there's also other uses, like you can also use it to keep track of whether components are bipartite and stuff like that. But that's just out of the scope of this lecture, so I won't present it. So you guys can go ahead and try these useful practice problems. And yeah, that's all I have for the lecture today.